this is Vivian and Alicia, and today we will be talking about a very fundamental concept of calculus called the chain rule. What is the chain rule? The chain rule is the derivative skill rule used for taking the derivative of composite functions. Now, if you recall, composite functions are basically functions within other functions, and we use the chain rule first to find the derivative of each outside function in order to multiply it to the derivative of each inside function, and this is going to give you the complete derivative for the entire function as a whole. In more formal terms, let's say you have the function y is equal to f of g of x, and if we take the derivative of this, so you get dy over dx is equal to f prime g of x times g prime of x. And that g prime of x is very important. It's what we call our hook-on factor. And that hook-on factor is the embodiment of the chain rule. We're basically taking the derivative of the inner function and multiplying it by the derivative of the outer to get the complete derivative. Let's tie this to something we already know called the general power rule. The general power rule states that if you have a function y is equal to u of x to the n power, if you take the derivative, you get n times u of x to the power of n minus 1 times u prime. As you can see, the hook-on factor or the chain rule remains in play here, and this is something that students always forget to put. The u prime, or your chain rule, will make or break your answer depending on if you remember to use it or not, so always apply it to the derivative. Now, when you're using the general power rule, it's very easy to take derivatives for very simple seeming functions, for example, 4x cubed. If you take the derivative with what you already know is very easy in your head, 12x squared, but we're going to show you why the chain rule exists for every function and why it's so easy to miss. If you take the derivative, you actually get 12x squared times dx over dx, and this is because you're taking the derivative of x in respect to x itself. And dx over dx is just 1, so it cancels out and you just get your derivative 12x squared. Now, this is why the chain rule always exists in every single situation, and this is why it's so hard to grasp, because the chain rule is always there. This is a mistake that students always make because they don't remember to search for the chain rule, and therefore the answer may come out as incomplete. Example of chain rule. If you have a function y is equal to 3x squared plus 2 all to the 4th power, if you were to take the derivative, you would take the derivative of the outside first, using the general power rule, like so, and you will multiply by your hook-on factor 6x. Now 6x is your crucial moment because it's your derivative of the inner function. So if you multiplied everything out, you get 24x times the quantity of 3x squared plus 2 all to the 3rd power. Your most crucial moment is your 6x because that's what's going to give you your complete derivative. If you didn't have that there, your answer would be much different than if you didn't notice it. Like many of the good things in life, the chain rule provides with us a proof that we can use to derive the chain rule from. Let's say you have a function y of u of x, your composite function. Remember, if we take the derivative of this, we take the derivative of the outer function and multiply it by the derivative of the inner function. So dy over du times d over dx. And so you can see the du's on both sides cancel, and you get dy over dx on both sides. If we assume y and u are differentiable and continuous at x, we can actually use the limit definition of derivative in order to find why the chain rule exists. So recall the limit definition of derivative. Of course, it requires knowledge of limits. Let's say you have limit as delta x approaches 0. So as the space between x values gets closer and closer, you have your delta y over delta x. And that, of course, is the slope of the tangent line, your derivative. We can actually rewrite the limit as delta x approaches 0 is delta y over delta u times delta u over delta x. Again, your delta u's cancel on denominator and numerator, and that way you get the same as the first row above. We can split the derivatives, so you get delta y over delta u times the limit of delta u over delta x. But what's different here is that because we took the limit of both quantities, we can actually rewrite the limit of delta u over delta x as du over dx because we're taking it in respect to x and we're finding du anyway. For the first part, it's not that simple, so let's refer to a graph. You have a graph, your x and c values, and your u of x and u of c. The space between x and c is delta x, the space between the y values is delta u. As you can see, as delta x approaches 0, delta u also approaches 0. So as the x values on the graph grow closer and closer, the u values also grow closer and closer. And so for the limit, we can say as delta x approaches 0, we can also say that's delta u approaching 0. And you write it as dy over du, and that's how we get the first part of the derivative proof. Now the chain rule also applies when you are deriving trigonometric functions. Let's say you have a function y is equal to 1/3 times secant squared of 3x. If we were to use the chain rule, of course, we can derive this. So move the power to the outside and you get dy over dx equal to 1/3 times 2 secant of 3x, so the derivative of the outer, and now you take the derivative of the inner. So derivative of secant of 3x is secant 3x tangent 3x, and now we take the derivative of the innermost function, which is 3. So multiply everything by 3. If you don't, your answer will come out different. If we clean it up, it's 2 secant of 3x times the derivative of secant. And finally, we can simplify further by factoring out secant of 3x, and you end up with the answer you see here. And this is the derivative chain rule application for trig.